All right. Ready to explore the world of real numbers. You've brought some interesting excerpts. Kind of reminds me of a math textbook chapter.
Yeah.
But that's what we're here for, right? Buckle up today. We're going deep into those number building blocks.
Yeah.
Euclid's division lemma and the fundamental theorem of arithmetic. Big names for, hopefully, big fun.
And they sound a lot more intimidating than they actually are. More than just some abstract theories, these concepts pop up in some surprising ways in our day-to-day lives.
Really? Like how?
Well, think about things like secure websites, or even how digital images get compressed. It all goes back to these fundamental ideas about numbers.
Okay, so let's unpack this. First up, Euclid's division lemma. Now, be honest, does this just mean long division got a fancy upgrade?
You're not far off. Remember how long division always leaves you with that remainder, smaller than what you were dividing by?
Yeah.
Euclid's lemma basically makes that idea official. Any positive integer divided by another will always give you a unique quotient, and crucially, a unique remainder.
So it's saying there's a specific way to divide any whole numbers, and you'll get a specific answer.
Exactly. And here's the cool part. That simple idea underpins something called Euclid's algorithm. It's a really powerful tool for finding the greatest common divisor of two numbers. You might know it as the HCF.
Oh, yeah, the HCF. Back in school, that was my go-to for simplifying fractions. But you said this has broader uses.
Way broader. Let's say you want to create those super secure keys for websites, the kind that keep your data safe, or encrypting data in general. Those processes often depend on finding these huge prime numbers. And guess what? Euclid's algorithm swoops in to save the day.
How so?
It helps us figure out if two numbers share any common divisors at all, even if those numbers are massive. That's crucial for generating those secure keys.
So, like, Euclid's lemma is the unsung hero of cybersecurity.
In a way, yeah. It's a fundamental part of lots of cryptographic algorithms.
Right.
And to see it in action, your excerpt had that fun example with the sweet seller and her barfis?
Yes, the one about stacking them.
Right. Picture this, a sweet seller with 420 Kaju barfis and 130 Badam barfis. She wants to stack them efficiently to use the least number of trays, but each stack has to have the same number of each barfis, like a tasty puzzle.
Okay, I'm intrigued. So where does Euclid come in?
Well, if we use his algorithm, we can find that greatest common divisor of 420 and 130, which turns out to be 10. That means boom stacks of 10 using the least amount of trays.
Elegant and practical. Sounds like Euclid had a knack for finding order in the chaos. But before we get too comfy, let's hit that other big theorem, the fundamental theorem of arithmetic. And that one, wow, even the name sounds serious.
It really is fundamental. If Euclid's lemma is all about division, this theorem is about multiplication. Basically, it says that every single whole number larger than 1 can be written as a unique product of prime numbers. Like each number has a fingerprint, but made up of these prime building blocks.
So you mean like 15 would be 3 by 5, 20 would be 2 by 2 by 5, and so on. Each combo of primes is like a number's unique code.
You got it. We call that prime factorization, and it's a lot more than just a mathematical quirk. This idea is behind a ton of really important concepts and applications.
Like, for instance, the source material mentioned irrational numbers. Those numbers that can't be written as simple fractions and their decimal expansions just go on forever without repeating. Does this theorem connect to that at all?
Totally. That unique prime factorization idea is a big part of why some numbers can't be neatly represented as fractions. It's like, imagine trying to build the square root of 2, but you've only got prime numbers as your building blocks. No matter how you arrange those primes, you won't get a perfect fit because the prime factors of its true value would repeat in a way that just doesn't work with simple fractions.
So they're like these rebels, these numbers, resisting any attempt to put them in a neat little fractional box. And it's because of their prime factorization.
Exactly. And when mathematicians want to prove a number like the square root of 2 is irrational, they use this really cool technique, proof by contradiction.
Yeah, I've heard of that. It's like you assume the opposite of what you want to prove and then show how that assumption just leads to a contradiction, right?
Right, spot on. It's a classic move in math. So we'd start by saying, okay, assume the square root of 2 can be a simplified fraction. But then using some algebra and those prime factorization properties, we hit a wall. That contradiction tells us our initial assumption was wrong. Your source material actually walks through a simplified version of this proof. It's really quite elegant how it all comes together.
So, to recap, we've got this powerful theorem that deconstructs numbers into their prime factors, and that even helps us understand these irrational numbers. But I gotta ask, what about real-world use? It's not like I'm proving theorems every day.
You might be surprised. This theorem actually pops up all the time, even in simple stuff. Remember when we talked about finding the least common multiple of two numbers, the LCM?
Yeah.
This theorem gives us a super elegant way to do that.
Wow. I never made that connection. It's kind of wild how something I learned back in, middle school has such broad applications.
It's true, and it doesn't stop there. This theorem is essential for things like cryptography, keeping our online info safe coding theory, even compressing those images we were talking about. Knowing how to work with prime factorization lets us make those processes way more efficient.
Okay, now that's just cool. This theorem is secretly running the show behind our digital lives.
You could say that.
But hey, before we move on, there was something in the material about the history of the fundamental theorem of arithmetic. Something about a prince of mathematicians.
Ah, right. So while people probably knew about the theorem in some form way back when, it was Carl Friedrich Gauss, often called the Prince of Mathematicians.
Catchy title?
Yeah, he was the one who gave the first really solid, rigorous proof in the early 1800s.
So even though the idea was out there, he made it official in the math world.
Exactly. Gauss's work on this theorem made it a cornerstone of number theory. It just shows how even these ideas that seem simple can have huge implications if you explore them deeply enough.
It's clear that Euclid's division lemma and this fundamental theorem, they're like the VIPs of the number world, and we've only just scratched the surface. But before we go further, something's been on my mind. The source material mentions something about how the way numbers are expressed, like their decimal expansions, is also influenced by these theorems.
Right.
We talked about those irrational numbers, how their decimals never repeat. Is there connection there?
You're right on the money. These theorems help explain why certain decimals decide to be nice and tidy, ending neatly, while others just keep going and going. Think about a simple rational number, one we can express as a fraction. If the denominator of that fraction only has 2 and 5 as prime factors, the decimal representation will always terminate.
So those prime factors, 2 and 5, they're like the bouncers of the decimal club, deciding who gets to stay and who has to keep moving.
That's a great way to put it. To get a terminating decimal, you need a denominator that's a power of 10 eventually, and the prime factors of 10, just 2 and 5.
Ah, makes sense. But what about the decimals that never end and they just keep repeating the same digits over and over, like 13? It's just 0.33333 forever, right?
Those are the rationals whose denominators have other prime factors. Besides 2 and 5, they're the ones causing a ruckus. Can't be expressed with a power of 10 on the bottom, so their decimal forms get stuck in that loop, repeating forever.
So it really all comes back to those prime factors. They're calling the shots in the world of decimals.
It's pretty amazing, isn't it? Prime numbers, divisibility. These simple ideas have such a huge impact on how we understand and represent numbers.
It's mind-blowing. We started trying to wrap our heads around real numbers, and we've found all these hidden patterns and connections I never would have guessed. Euclid's division lemma, that clever little division trick, the fundamental theorem of arithmetic, breaking down every number into its own unique fingerprint. Even those rule-breaking irrational numbers and what's going on with those decimal expansions has been quite a ride.
It's been a pleasure diving into these ideas with you. And remember, this isn't just some theoretical stuff. These concepts are the foundation for so much, from cryptography to computer science, even music theory. The world of numbers is full of these hidden depths, just waiting to be explored.
Absolutely. And I'm sure you've given our listeners a lot to think about today. Like we were touching on earlier, if prime numbers are infinite, does that mean there are infinitely many irrational numbers, each with its own one-of-a-kind decimal fingerprint? Something to ponder. Thanks for joining us on this deep dive into the fascinating world of real numbers. Until next time.